You know what? I just didn't think this lesson was quite long enough, so let's return back to our initial discussion about Gabriel's horn. So it was the warm up exercise which kind of fueled the whole entire discussion for these improper integrals. So what we had was the region 1 over x, this infinite region starting from 1 going off to infinity, revolved that thing around the x-axis. It generated this thing that we're calling Gabriel's horn. And what we wanted to do is we wanted to find the volume of that thing, and that's the part that we hadn't done yet. So all of the stuff that we've done for integrals, like volume, like arc length, we can still do with these improper integrals. Does it mean that we're going to have an infinite volume or a finite volume? We'll just have to do the math and see. So let's do that here on Gabriel's horn. So we want to, again, like we've already set this thing up, I can scroll up here and I can take a look at, my goodness, does this make you dizzy? I don't even know. All right, so here's the improper integral that we set up, and so this time I'm actually not going to make you sick. I'm just going to flip straight to it. So it's pi, definite integral from 1 to infinity, 1 over x squared with respect to x. Okay, so this a little bit easier to digest, not as nauseating. So for this particular example, 10, we have our volume being equal to definite integral, oh yeah, don't forget your pi, definite integral from 1 to infinity of 1 over x squared with respect to x. And then I can see quite obviously that we've got an improper integral because we've got this upper limit which is infinite. So we're going to take it out, replace it with a b, and then take the limit of this thing. So limit as b approaches infinity, throw our pi still in here, definite integral from 1 to b, x negative 2 dx. All right, now we're ready to integrate this thing. Carry down our limit. B goes to infinity. Still some sort of pi. Antiderivative x to the negative 2 power is a negative 1 over x. And we'll evaluate that from 1 to b. Pretty sure that we've seen this before. Remember that this thing is a p-series, and that p-series, when that p is greater than 1, this thing converges, this thing should converge. What does it converge to? Well, we've got this little pi thingy in there, so it's going to mess things up just a little bit. Limit as b goes to infinity, pi times, actually let me bring this negative out here too, and then evaluate this as 1 over b minus 1 over 1. All right, and then evaluating the limit, this part here is going to go to 0, 1 over infinity, and the other part is going to go to negative 1, so I have a negative pi times a negative 1, which gives me pi. Here we're seeing this thing again, pi. Our volume converges to pi. In other words, let's come back up here to our picture of Gabriel's horn. Even though this horn is infinitely long, it has a finite volume, and that volume is getting closer and closer to pi, okay? So now the next thing is, I'll actually want to look at the surface area of this thing. Oh, let's go back to the PowerPoint. It looks a little bit better. Okay, so while the volume of Gabriel's horn converges to, pi like we just showed, what about the surface area? The surface area is not something that we've talked about how to do, so I'm going to discuss how to do it. Like it's been taken out of the, it's in, let's say, a college course for calculus, but it's definitely not on the AP exam, so it's not something that we're going to have to duplicate. So I'm just going to run through some example on how it's actually set up so you can see what it actually is, what the formula is and whatnot. Okay, so it's based on what's called a frustum of a cone. It looks kind of like a lampshade. And here's what the integral looks like. So S for surface area, we got a 2 pi times definite integral of this r of x function. R of x, as we're going to see, it's really technically the average radius, and we're going to interpret that as the distance away from, our function's distance away from our axis of revolution. In most cases, that's just going to be our function, right? Unless it wasn't actually the x-axis that we're going to revolve it around, but in this case it is. And then it's going to be multiplied times the square root of 1 plus f prime of x squared dx. What's that? That looks familiar when I take the integral of that. I do believe that that is the arc length. That's the arc length formula there. Okay. So again, not something that we have to have memorized, but we're going to use that in order to demonstrate, like to find the volume or the surface area of this thing. Whoops. Okay, so that's what, this is the general surface area formula for a frustum of a cone, and you can see that those two parts playing out within this definite integral. Okay, so here's a kind of a set of pictures to go along with all of that. So we're going to set this thing up for the Gabriel's horn example. All right, so we're going to find the surface area of the solid formed by Gabriel's horn, just like we did with the volume, right? Okay, so let's come down here, and we have a couple of things that we got to do. So we said that this part here is essentially going to be our function. So this is going to be f of x. It's the distance away from the axis of rotation, and for us, that's just, you know, that's just our function, right? As if I had this little representative rectangle there. All right, and then we'll also have to take the derivative as if we're going to do the arc length on this thing. So our f of x is equal to 1 over x, which is x to the negative 1 power, and then its derivative would be negative 1. Why write that down? X to the negative 2 power, or if you prefer, negative 1 over x squared. Okay, so now we're ready to set up an integral for the surface area. It has a 2 pi on the outside of it. Definite integral from 1 to infinity. That's going to make this thing improper, so we'll have to fix that. We have our radius function, which is 1 over x, that we're going to multiply times the arc length formula, which is 1 plus negative 1 over x squared dx. All right, and then I'm just going to fix this. It is improper, so I'm going to get rid of this guy right there and replace it with a b. So this will be equal to a limit as b goes to infinity. Throw a 2 pi in here. And our definite integral from 1 to b. Rewrite everything, make it look pretty, and then make this 1 plus 1 over x squared dx. Okay, we've taken our integral, turn it into a limit, and now it's time to try to evaluate it. And then we get stuck. The reason why we get stuck is that this thing, not going to be able to evaluate. Not at all. There's no, like, easy antiderivative. You could try to, let's say on the inside of this, get a common denominator and see if maybe that thing gets to come out of it. Problem is that none of that stuff works. You can't find an antiderivative. And so what we need is what we're going to call a comparison test. And what that means is, like, we're going to take this integral and we're going to compare it to something that we already know something about. How does it compare? And essentially it's going to go like this. Is our integral, is it smaller than a convergent one, so it has to converge, or is it bigger than a divergent one, which makes it diverge? So let me summarize that stuff back here in the notes. These comparison tests, and these comparison tests are going to come back to us again whenever we do our infinite series. So sometimes it's absolutely impossible to find the exact value of some sort of improper integral. So what we're going to do is we're going to compare it to something that we already know. So before we even put actually what the comparison test is, let's take a look at the picture that's over here on the right-hand side. So notice that we've got this f of x function. It is completely over the g of x function. And so you got two possible cases here. Let's say, for example, that f of x, like the area under this unbounded area under this curve, let's say it converges. Then what conclusion can you draw about the g of x function? Area under that is smaller than one that converges, so therefore it has to converge too. So there's our first one. F and g be continuous functions with f of x being greater than or equal to g of x, which is greater than or equal to 0 for some value of x bigger than a, right? So at some point, all of this it could be like x equals 1 or something like that. Everything beyond that, all of this stuff is true. If that's the case, if the definite integral from a to infinity of f of x dx, if that thing converges, then so does the one involving g. In other words, if you are smaller than a convergent improper integral, then your new integral is also going to converge. Okay? And now the other case is this. The other case is, well, what if I have to flip it over and look at the g of x function? What if g of x actually diverges? And we're looking at f of x, which is bigger than that. If you are accumulating more area than a divergent improper integral, then you're also going to diverge. And so that's what the second comparison test is. So again, f and g are continuous functions, and we're saying that f is still greater than or equal to g of x for some value of x greater than or equal to a. And this time we're going to say we're looking at that bottom function. If that bottom one diverges, then the top one also has to diverge. And the way we're simplifying that, in layman's terms, it is if you are greater than, if your improper integral is greater than a divergent integral, then your integral also diverges. Okay, so those are the two comparison tests. See if you can wrap your head around that, and then we're going to see if we can apply that back here to this problem. We want to compare this to something that we already know either converges or diverges. And the secret lies right here in this piece. And I just noticed now that I rewrote that incorrectly. Again, nobody spoke up. This should have been a 4, but I can fix it perfectly. It's as if it was never wrong, right? Because we squared the square, so it should have been a 4. All right, so let's think about this value for a second. First of all, I'm going to take a square root. So I know that it's going to be positive, right? I'm taking the square root of something. This thing is positive. Okay, not only is it positive, think about the x value. The x value is something that it's starting at 1 and getting bigger and bigger and bigger. So what happens to this value that's right here as x gets bigger and bigger and bigger? Well, that one's going closer and closer to 0, so this whole entire square root is getting closer to 1. It's bigger than 1, but it is getting closer and closer to 1. So we're going to say that this thing is not only positive, but it's greater than, where's my green? It's greater than or equal to 1. Does that argument make sense? So we're going to take, basically, we're taking this whole thing right here, and we're multiplying it by something that's bigger than or equal to 1, which means that our integral, the one that we are trying to solve, this improper integral, the original one, I'll write it that way, 1 over x square root of 1 plus 1 over x to the 4th dx, I wrote it properly this time, has to be greater than or equal to 2x, not 2x, 2 pi, definite integral 1 to infinity again, but just the 1 over x. Right? We got rid of the square root part because basically we're multiplying it by something that's just a little bit bigger than 1. So our integral, the one that we're trying to evaluate for the surface area, has to be bigger than the one that's over here on the right. And now what's going to come into play is our comparison test. And it's actually this second case here because we're comparing it to something that we already know diverges. And ours is bigger than a divergent one. How do I know it diverges? Because this is that p series which has a power of 1. So this one here diverges. So this is diverges. And we did this exact example maybe 1 or 2 times previous to this because p is greater than 1. All right, so now I'm going to wrap this thing up and say that our original one also has to diverge. And the reason why is because it is greater than a divergent one for some value of x, and that x value is greater than 1. So therefore, 2 pi 1 to infinity 1 over x square root of 1 plus x squared dx must also diverge since it is greater than or equal to a divergent improper integral. What the heck does all of that mean? It means that Gabe's horn has an infinite surface area All right, let's kind of try to digest all of this. Let's see what the implication of all of this is. We were able to show way back over here that Gabriel's horn has a finite volume. Its volume converges to pi, right? And then based on this formula for the surface area of a solid of revolution, we were able to show that its surface area diverges. Its surface area is infinitely big. What it means is this. It means that if we take this shape right here, we could actually fill that thing with some sort of paint, right? It has a finite volume. I could fill it up with like pi, exactly pi cubic inches of paint or whatever the heck unit that we might be using. However, even though I could fill it up with pi units of paint, cubic units of paint, I could not paint its surface. And this is what's known as the painter's paradox. I could fill it with paint, but I couldn't paint it. Whoa, that's amazing, right? That's one of the super interesting things about this thing that we're calling Gabriel's horn. Okay, hopefully that didn't blow your mind too much because we've got one more example, just one more example to look at. And again, it's going to involve these comparison tests. So show that the improper integral, we can definitely see it's improper, from 0 to infinity of e to the negative x squared is convergent. Well, to show that it's convergent, I need to be able to either take its antiderivative and then use the rules that we've established for improper integrals. Problem is I can't do that with e to the negative x squared because it does not have an antiderivative that we know. When we do our series lesson, we'll be able to find an antiderivative, but it is infinitely long. So you can't find a nice, neat, closed form antiderivative of that. So what we got to hope for is something like this, one of these comparison tests, right? And if it's got to converge, if we're showing it's convergent, we need to show that it's smaller than something that we know converges. And so I got some graphs for you. So here's this graph. Ignore the typo that's on the label for that thing because it's not e times x to the negative x squared. I don't know why that's on there. Anyway, we're going to compare it to something that we know converges. I'm pretty sure that we did this graph in a previous exercise is e to the negative x. And notice that the one that we're looking at here, which is e to the negative x squared, it's not always underneath the green function, which is e to the negative x. But that's okay, because it is always underneath it to the right of 1. And that's all we needed it to be true for this particular comparison test. As long as it's ultimately below it for everything greater than or equal to 1, then we can use this comparison test. Okay, so that's exactly what we're going to do here. So we're going to show that the definite integral from 0 to infinity of e to the negative x is convergent by comparing it to this other one, which is e to the negative x. So what we want to know, notice that e to the negative x squared is less than e to the negative x for x greater than 1. And that's what we needed to be true. And we're going to show that e to the negative x converges, and since ours is underneath that, the green one, it's underneath that green one, then ours also has to converge. Right? So that's what we're going to look at. We're going to set this up as example, the last one, hopefully. I don't know, maybe there's going to be a secret video and have another 10 or 15 examples. I don't know, you'll just have to look for it. We've got definite integral from 0 to infinity of e to the negative x squared dx. And we're going to show that that thing is less than or equal to, what the heck is that thing? Come on. Definite integral from 1 to infinity of e to the negative x dx for x is greater than or equal to 1. All right. And so now this other one, this is the one that's improper. It's improper, so we're going to have to fix this one here. So we've got the limit, writing with a highlighter, the limit as, I'm going to take that one out and replace it with a b, approaches infinity, definite integral from 1 to b e to the negative x dx, which we've already done this a couple of times. I want to say its antiderivative is negative e to the negative x, evaluated that from 1 to b, which is equal to negative e to the negative b minus a negative, so plus e to the negative 1. This part here, the first part, is going to cancel out because e to the negative b is going to get closer and closer to 0, and we're left with e to the negative 1 power, which is essentially 1 over e, which converges. Right? Okay, so now I'm just going to draw my proper conclusion here and say that since e to the negative x squared is less than or equal to e to the negative x for x greater than or equal to 1, and the improper integral from 1 to infinity of e to the negative x dx converges, then ours also has to converge from 0 to e to the negative, no, what am I doing there? That's infinity. E to the negative x squared dx. That's the comparison test in action there, all right? So again, we're going to see these kind of comparison tests again in our series lesson. Now, if you're a little bit confused about the fact that this one had a 0 and this one had a 1, we'll just understand this. Like, as far as some sort of series goes, I would have an additional piece that I would be adding to this. Let me change this color over here. This is the piece I'd be adding to it. And you can obviously see that this individual little piece is finite. I'm going to take whatever this finite area is, and I'm going to add it to something which also converges, and so it's still going to be finite. And so that's why it doesn't matter that it still doesn't start at 0. This one's going to start at 1. Again, up here in the comparison test, it says as long as these inequalities are true for some value that's greater than or equal to a. All right, that wraps up our lesson here on improper integrals, where we're able to evaluate improper integrals using some sort of limits. And we know that we have a couple of different cases. The obvious ones where we have the upper and lower limits either being infinity, or maybe we have one that's in disguise where the upper or lower limit or something in between is an improper integral. I mean a vertical asymptote. Okay, so whenever you're giving this homework a try, definitely give that homework supplement, which has an AP question, a shot.